We will begin another subject which you may not all have direct interest in the audience, but it is something that you should know because it's likely to happen in our country seriously. I have titled it as subsonic to supersonic combustion, from the more known to the less known. Here again, I just want to emphasize to you that I have been associated with this subject for about 30 years. The DRDO started its work on looking at supersonic combustion late 80s, early 90s, and similar thing was done in ISRO, and ISRO has been successful to fly a supersonic ramjet engine, and the development in DRDO has gone through a good free jet test result, and some of it I will bring out. In many of the technical deliberations and discussions, review committees is involved. So I will bring to you some bit of known knowledge close to what has happened. Alright, I want to begin by talking about premixed diffusion, differences, jet diffusion, flame diffusion and premixed. More as an intro, but you may have heard about it, but we'll quickly browse through it. Gas turbine main combustion chamber, afterburners of gas turbines, ramjets transition to supersonic ramjets. I want to trace the changes which take place from gas turbine to supersonic ramjets. And then we look at issues of scramjets in terms of geometry, aerodynamics, flight boundary, fuels, injection system, injection, mixing, combustion, all that as a traditional part. You can edit it appropriately. This was some other presentation to a group of people in which the subject was something like stoves to supersonic combustion. So I begin with stoves. It's premixed combustion here of LPG. Whether it's here or here is the same. I just look at a Mach number, it is subsonic to extreme extent, very low velocities. And the points when you are looking at combustion are pressure and temperature, initial temperature, 1 atmosphere, 300 K, both cases. Well, this is something we have looked at significantly earlier. The only additional point I want to make are these. If you take hydrocarbon air 0.4 meters per second, hydrogen air 2.5 meters per second, and you can also have premixed diffusion or partially premixed situations, and we should keep in mind that. Of course, diffusion flame, which is well known. Okay. The point I am making here is the reaction zone is smaller for premixed condition compared to diffusion conditions. We had a video, so I thought I will play that. Hopefully, you will see how the flames are smaller and we can draw a conclusion. You see, the flow rate is the same. Power is the same, and power is the same is more appropriate word to choose. The flame volume here is much smaller than the flame volume here, and heat release rate is much higher in this case compared to this. You may ask a question, what does it mean to this? When you are looking at subsonic combustion, premixed flame, you can afford to do premixed flame. You have a choice, you can also do diffusion flame. But when you look at the supersonic combustion, you look at diffusion flame as the only alternative for good reasons which we will discuss later. So we go to gas turbines. Gas turbine main combustor, which is used on aircrafts, and flight Mach numbers up to 3. Go from 10 atmosphere to 40 atmospheres. Temperatures, inlet temperatures are anywhere from 450 to 650 Kelvin depending on the compressor pressure ratio, and that is what this tells you. The Mach number in the combustion chamber has moved to 0.25. And you must also know that you must complete the combustion in a certain residence time, that's typically about 5 milliseconds. And if you look at civil aircraft, most civil aircraft has 0.85, excepting when you go to Concorde, which is no longer flying, Mach number 2. Military aircraft go up to 2.5, and SR-71, designed by Kelly Johnson, Mach number going up to 3, and which runs quite a bit an afterburner at the outer limit of the flight Mach number. You look at the combustion system here, which is for the afterburner. Main combustion system is here. Afterburner is the systems which use this can go from Mach number 0 to 2. The pressure inside the jet pipe, the afterburner, is 3 to 5 atmospheres, because pressure here is 10 to 40 atmospheres. It drops the pressure in flowing through the turbine, and therefore the pressures here are lower. The inlet temperatures go up to 1000 Kelvin, because the temperatures here are about 1400 to 1500 Kelvin, and they drop down here to 1000 Kelvin. The Mach number here is 0.33. They have moved from 0.25 to 0.33. Then we look at ramjet. Ramjets function only from about Mach 2 onwards, maybe up to 3, 3.5, but usually up to 3. And you have a since its Mach number is 2, and the combustion process has to occur here in subsonic conditions, you have a device a compression system here, shock system here, to reduce the Mach number. An intake which is called external compression intake. Sometimes it can be mixed compression intake, internal compression intake, and so on, which reduces the Mach number at the entry to the combustion chamber to around 0.3, and you add fuel, acceleration occurs here, and you go to Mach 0.6. The holes refer to the fact that there might be buzz or instability. To remove the instability, you have holes which absorb the acoustic energy in some way. We must remember, this is not self-starting. That means you can't run a ramjet to start off. So you must accelerate it to Mach 2. And this stagnation pressures, here go from 11 to 15 times ambient pressure, because of the Mach number. And air inlet shocks bring down the pressure to about 3 to 5 atmosphere in the combustion chamber. The pressure in the combustion chamber from the air that is dumped into it is 500 to 750 Kelvin. Mach number is 0.4. Combustion residence time still remains at 4 to 5 milliseconds. At this stage, you may ask, is the gas turbine combustion chamber self-starting? Is it self-starting? Quite self-starting. You need a starter for that. So you need to run up the rotating system with additional device, which can be electric starter or something else, and you bring it up to some speed, rotational speed, and then inject the fuel, because in the combustion chamber there must be air. That air can only be ingested, and it has to come from the atmosphere. So to run up the system such that you get enough airflow into the combustion chamber, then you begin to inject fuel and spark it so that you have combustion going on, and then it accelerates to its nominal speed. I just want to bring to your attention a feature which you must have read in newspapers, that Indigo Airlines has a problem with their engine. They have to replace the engines quite frequently, and one comment, which I don't know how valid it is because the Indigo pilots use the engines little more roughly, shall we say, compared to what is expected. That's probably true, but my personal experience is that they use the takeoff period at a much faster rate than what happens with many other airlines. So you may ask me, what is that got to do with the discussion here? I may tell you a bit of experience which as a part of development which took place about 30 years ago. There's an aircraft called Canberra aircraft in the country, which was used by services. That Canberra aircraft has 3 cartridges, solid propellant cartridges. So the pilot accelerates up to some speed, and then he runs the cartridges, it spins the turbine system, and then of course fuel injection takes place and so on. the electric starting system takes it to some level, and then this cartridge has to come in to bring it to the next level. It turned out over a period of time, the pilot used to push it at a much lower RPM. It's supposed to be at 25% of the RPM or 30% RPM. Now he was not accelerating enough, so the solid propellant cartridge little at an earlier speed. So one might think, oh, what is it? It doesn't matter, it's not a difficult task. But it's a difficult point. I'll tell you why. You introduce the hot gases onto the turbine blades to spin them. Now you are supposed to do it now as per the guidelines of the designers at a certain speed. Then it accelerates. But if you do it earlier, you are essentially shocking the turbine blades. So they discovered over a period of time that the turbines had to be replaced at a much lower time than the earlier situation where they would have no such problem. So they referred it to us, and what we discovered after analysis is that the propellant cartridge, while maintaining to the standards, was at the lower end, which means the fuel fraction in the solid cartridge was more than what was expected in the nominal condition. Because of which the performance was lower, and therefore it was never spinning it properly. They were trying to do it at a much lower speed than otherwise. Well, they did some corrections, but then Canberra aircraft is now outdated, so it's not there. So all that I am trying to tell you, that even starting sequences for gas turbine engines had to be designed carefully, because the spinning takes place, and afterwards when you inject fuel, you cannot inject fuel much earlier. You have to inject only at some stage. And if you do it earlier, you are shocking the turbine blades, and the life of that system may come down. Okay, so that's just by the by. We move to the next. Yeah, sure.
Can you comment on the chamber pressures on ramjet? Like 3 to 5 atmosphere seems to be a low number compared to the other liquid engines.
So why do you say that it is lower number?
If you are considering the normal rocket engines,
sure. The afterburner, are you comfortable with 3 to 5 atmospheres?
Yeah, that is okay. I am telling about that combustion pressure is only 3 to 5. P combustion is only 3 to 5 atmospheres.
See, what happens is there is a loss of pressure in the recovery through the shock system. Okay, that's why the pressure is not necessarily very high here. And you see, in this design, I am showing it in some manner, but in actual systems, the pressures could be even lower. It's all done at high altitude. See, it has to go to at least couple of 1,000 kilometers. No, not 1,000 kilometers. About 100, about a few kilometers above, this begins operating. Once it operates at several kilometers, the actual pressure is lower. So the pressure inside the combustion chamber is therefore lower. You understand the thing? Okay. So look at the operational range of a ramjet. You can make a simple calculation, system calculation, and this quantity is called a thrust per air flow rate. It's a dimensionless quantity. It's a measure of compactness of the engine. If you are able to get the same thrust at a lower mass flow rate, the thrust per unit flow rate is higher. So you will discover that that number goes to a large value in a Mach number range of 2 to 3. So this is in fact the appropriate range that you should look at. But if you add inefficiencies into the system, you can actually show that no ramjet ever starts at less than near about Mach 1. So you have to keep it at Mach number more than 1, and typically it's Mach 2 to 3, and therefore you have to accelerate the ramjet to that speed and then allow the ramjet to function. And there are ramjets which are functioning like that, solid fuel ramjets, as a part of missile system. One project called Akash uses this such systems. So what I am saying here, as Mach number increases, bringing down the Mach number through the shocks to subsonic conditions at the combustion chamber will become more and more inefficient. Adequate energy addition difficult to have an efficient propulsion engine, and hence Mach number should not be brought down too much. If you go to higher Mach numbers, it's far more difficult to bring it down because of the inefficiency of the shock system and also some other features. So, this leads to scramjet combustion chamber, where you say I do not want to reduce the Mach number to subsonic conditions, but let it remain in supersonic conditions, and therefore I burn the fuels under these conditions. This is the logic which is put together. Actually, you can show that when you go to increased Mach numbers, the thrust per unit flow rate goes down so sharply, with inefficiency included, that it no longer provides adequate thrust. Therefore, it is compulsory to make sure that you go to reducing the Mach number to near supersonic conditions. So, I am assuming that we know why we are in supersonic combustion regime, and we are looking at the issues. Some of them, other points also may get covered. We look at flight boundary, geometry, aerodynamics, fuels, injection system, ignition system, mixing, combustion performance. Since ramjets and scramjets are not just starting, they need to be brought to speed. In both cases, one can conceive of airdrop from an aircraft with a maximum speed of about 0.8, taking the system to Mach 5 or 6 in the scramjet is essential before scramjet begins functioning. This is something which you can understand. However, rocket as a propellant system is considered very vastly simpler. Rocket delivers the scramjet vehicle to altitude and the right attitude. Altitude is typically about 30 to 40 kilometers, Mach number 6 to 7, and sometimes even up to 100 kilometers. When you go to that altitude, you can go to Mach 10. This is the case of X-43A. You see the altitude is close to 100,000 feet, 100 kilometers close to, and the 30 kilometers roughly, and then you will find Mach number of, in this flight Mach number is 9.6 or so, 10, and its operating period is about 6 seconds, demonstration, it comes down. Generally, scramjet operate at a single altitude over the duration, since change in altitude changes the combustor conditions significantly. Assuming that the system has been tuned for one flight condition sensitively, increase in altitude at the same Mach number reduces the combustion chamber pressure and degrades the chemical reaction time. That means the reaction time will be larger. Lowering the altitude causes increased pressures as well as more hostile thermal conditions. The same Mach number, lower altitude means you have more strong shocks and you will have problem, and stronger pressures, and therefore it is more hostile for the hardware. However, with the availability of fast response control systems, it may be possible to change the scenario, but it is too early to say that in the development of the total systems. How will the geometry look like? It usually the way you have a front shock and system, and then you reduce the Mach number to levels you think will be appropriate for the combustion chamber, introduce fuel, combustion takes place, then you have a nozzle, and therefore you get pressures on the system to produce the thrust. This is the broad approach to handling the propulsion. Most usually the geometry here is rectangular, as you see, integrated into the vehicle and not quite circular. So, one might ask a question, while combustors in gas turbine engines, both main or afterburner, as the ramjets are circular or annular, axisymmetric in shape, but the shapes of scramjets are rectangular. Why is it so? So, while gas turbine engines can be chosen from several choices, you can make the same aircraft fly a General Electric engine, a Pratt & Whitney engine, or a RB200 engine, whatever, you can make a choice. And they can be integrated into the aircraft appropriately. But for hypersonic vehicles to be conceived, the vehicle that needs a certain lift to drag ratio with wing shapes and supersonic aerodynamics at the front end, which can enhance or spoil the propulsion very significantly. The aerodynamics content in a hypersonic vehicle is a very significant part of the total propulsion. So, the engine has to be hugging the vehicle. It helps to design a scalable unit to help reduce the development. Now, thrust and drag are close to each other, and any reduction in drag can be thought of as having generated more thrust. It is not quite so true with, basically it is fundamentally true with any propulsion system, but it is you have range, the thrust to drag is much larger in the case of other engines and aircraft propulsion systems and flight vehicles as well. Therefore, you have a choice there, but you have very little choice here. I want to liken this to what's called Ardhanarishvara. There are temples where you have Ardhanarishvara. It's integrated. So, that's the point. Little more about geometry. You have a rectangular combustion system. The air enters into the combustion system at Mach 2 to 2.5, something in that range. Temperatures in this range of 1200 to 1500 Kelvin. Pressures are low, 0.5 to 1 atmosphere. And you have a system here to enable you to create shocks, and you can introduce combustion systems so that you have a recirculation zone. That's the idea of creating a geometry like this. You can inject it perpendicular to the stream or along the stream, transverse injection, axial injection. All of them will have some degree of shocks. You have variety of designs which got developed over a period of time, pylons and so on. And one strut design which was developed in 1964 by Marquardt company. You will find a good report on that subject. So, the ideas have been floating around for a long time. They couldn't be brought up to the development, could not be brought out so that be tested for almost now say 40 years in some way. It's only about 2000 plus that things have happened. The flow is decelerated to low supersonic Mach numbers, typically a third of the flight Mach number. That's why Mach 6 means Mach 2 for the combustion chamber. And the combustion process has to be initiated at these conditions. Now, typical static temperatures, as I mentioned earlier, is about 1200 to 1600 Kelvin, and pressures half to 3/4 of an atmosphere. The static pressure crucially decides the combustion process. While higher static temperatures are appropriate for ignition, the low pressures may hinder the ignition process, and the steady combustion demands a larger combustor volume, and this is a feature which may be very critical for scramjet. Everything matters a whole lot. You can't be excessive in anything. Ignition can be helped by several means, including pyrophoric. That means you inject a liquid, it ignites with air, and therefore it is pyrophoric. But steady combustion demands a combination of distributing the fuel injection over the cross section, and a small subsonic zone may dominate, and it holds the flame steadily. This is a debate which has taken place over a long time. Supersonic combustion, you say, should there be any subsonic pocket at all? Debate has gone on. And if there is a subsonic pocket, can you call it supersonic combustion? Now, it's a semantics. In some way, in the flow domain, if a part of the flow is subsonic, be it so. It doesn't matter really. So, this is the argument, counter argument to that. But this argument can go on in academic settings, but flight vehicles at Mach number 6 cannot happen unless the combustion occurs in supersonic mode. What are the fuels which are possible to use in such systems? Early and space-centered efforts use hydrogen as a fuel. Hydrogen as a gas is easy to burn and is achieved more easily than hydrocarbons. But unfortunately, it is lower in density, can be used only for short missions. If you have a long burn duration, then you have to carry a lot of hydrogen, a lot of volume. It is not possible to design a system. It's nothing like you can do one thing or the other, like in rockets. You don't have too much of choice. However, use of liquid hydrocarbons, say kerosene, calls for attention to atomization, tracking vaporization processes through the combustor. So, you cannot escape atomization in such situations. Some higher density fuels like JP10 have been tried out when available. This is very commonly available in US and Russia and so on, including in China, but it is not available in our country very much. Some development efforts are going on, but still not adequate. There is something called endothermic fuels. These fuels decompose on heating without becoming soot. The problem with kerosene is, if you use that as coolant, then it decomposes to soot. It deposits in the pathway, therefore hinders the flow of the liquids. It is a serious problem. So, the choice is that you have to limit the cooling, if at all, or you have to look for other fuels, and these endothermic fuels are a choice. Again, this requires development. Some development has taken place elsewhere, but it also happened in our country. This is one area which is open at the moment. How do you inject the fuel? Fuel needs to be injected in the combustion chamber at a supersonic flow inside with large enough static temperatures and much larger stagnation pressures. Avoidance of hot pockets near the valves implies that the fuel be injected from centrally located struts. You have struts like the one that I showed you about Marquardt. That's a good design in terms of how to inject the fuel. Typical velocities in combustion chambers are about 1 to 1.5 km per second. Mach number is 1.4 to 2, even though inlet flow is Mach 2 or Mach 2.2, because there are always struts which create shocks and therefore reduce the Mach number. Is to be ensured that the combustion occurs in a graded manner, not too fast, not too slow. If too fast, the pressure rise rate may cause inlet flow to be influenced. Suddenly heat release will push the flow, so the shock will move back into the air intake, and the whole flow process gets completely affected seriously. If too slow, the heat release process would lead to poor combustion efficiency. So, we need to go through a narrow track of not being too slow or too fast. I am saying that very specially because many times people talk about this problem on a subject which probably we will debate tomorrow. I will bring it up tomorrow. So, it turns out that mixing between the fuel and oxidizer is a crucial issue. A lot of work has been done by researchers over a period of time, and the summary is that the length to the injector diameter for 90% mixing goes all the way, very poor injection, parallel injection gives you 700, and the lateral injection can bring it down to even 40. Typical distances of 100 may not be unreasonable. And by reducing the injector diameter, you can reduce the mixing distance, and if your injector hole diameter is about 0.5 mm, which is a standard dimension, one unit distance not more than 75 mm for mixing and about 300 mm for parallel injection. So, either way, it's not a bad issue. The typical combustor length will be around a meter in large engines. If you look at the processes that occur inside the supersonic combustor, is shown here. You have a wedge and you may inject the fuel here. Because you have a wedge, there is a recirculation zone in this domain, and this is a standard way of doing it even in afterburners. So, you do the same thing here, but you must limit the size so that the pressure drop, because the presence of this must not be large, otherwise you lose the stagnation pressure and therefore you lose the performance. Now, the flow will actually have a mixing layer, a supersonic mixing layer, a subject which has been debated, discussed in the last 20 years a whole lot, and the mixing layer thicknesses are small because the velocities are large, and you will find a diffusion flame occurring in this domain, because the fuel comes here, it burns and holds steady the flame, and further combustion takes place as the flow goes through this. If it is gaseous fuel like hydrogen, then the combustion process begins right away. If you inject kerosene, then some bit of vaporization is important, and then combustion has to take place. So, if you take the total time for combustion, it is composed of ignition time, vaporization time, mixing time, and reaction time. All these are important. And sometimes a simple scaling will tell you what may acquire greater relevance in design. If you look at ignition time, it goes as inverse of pressure and favorable in terms of temperature. As temperature increases, you will find this time comes down, but pressure is lower, this time increases. So, it in fact is so critical in the case of the ISRO vehicle. There are lots of debates whether the auto ignition will take place or not. They wanted to ensure that such a problem will not create difficulties in the first flight. Sometimes the first flight is very crucial. If you succeed in the first flight, your confidence level is up, and if you have any problem in the first flight, you really morale is down in some way. And when you are looking at new technology, it is all the more important to make sure that you succeed right in the beginning. So what was you have a mixture of liquid oxygen, liquid or gaseous oxygen and hydrogen, and you spark it and create a flame structure like a small rocket, and this comes through in this domain. You can also inject fuel is also injected in other places. Because you have a hot gas stream, a rocket kind coming out, it turns out that the ignition process is very stable. So to start ignition, you do that. Then you can ask a question, should we turn it off or should it be remaining there all through? Because it is not obvious that the ignition will get sustained at the pressures and temperature conditions. So it turned out in the case of the ISRO flight, they turned off the this system, ignition system, and the combustion process sustained on its own. So it was a good experience to know that ignition was the purpose for which it was used was served, but was not required beyond ignition. In the case of liquid, you look at vaporization, and vaporization which will go like d squared by k, evaporation, standard expression which you have learned till now. And mixing. Mixing is a difficult subject here. There is a mixing layer here. It grows in some manner. It is a very complex study has been going on for a long time. Mixing layer related to velocity difference divided by some mean velocity and so on. And there is a compressibility effect which has to be accounted. I do not discuss that here, and the difference in velocity is what is required to tell you what the time of mixing is. Reaction as usual goes inverse as the p square of bimolecular reactions, and it is of E by RT is the standard thing. For high temperature reactions like scramjet, E ignition by R and EG by R are relatively small. I want to bring to your attention something. See, whenever you are looking at chemistry, you are looking at chemistry at 300 Kelvin, pressures of 1 atmosphere and so on. The pressures are same in the case of supersonic combustor, but temperatures are very high, 1000 K plus, 1500 to about 2800, 3000 Kelvin is the temperature range. So the question that sometimes is asked, is the chemistry which is valid for 300 K to 3000 K or 2400 K, will that same thing be valid in the case of 1500 K to 3000 K? Now, the key point to notice is that as temperature increases, E by RT comes down, and you will find that the several steps of the chemistry which are relevant here are not so important at high temperature. So, it is important to keep this in mind. Foreman-Williams has done some work using opposed jet diffusion flame at high temperatures. So, some changes in chemistry may be required, but when you go to fluids like kerosene, you are always in trouble because the droplet vaporization after it takes place, the molecule is so complex, the decomposition of that to various segments in the presence of air is not so very well understood. So, quite often the chemistry that is chosen is a two-step chemistry. You take any hydrocarbon, it goes to CO2 plus H2, and then the CO gets oxidized to something else. Is another approach which has been chosen, and it is what has been practiced in many places. Okay, and but even I must say that in the case of liquids, the vaporization time is the key for most scramjets, because the moment it evaporates, you can take reaction time to be very small. It does not matter, temperatures are very high in most zones downstream of this place. See, inlet around 1500 K, as you keep going downstream, it turns out that the mean temperatures are higher, so reaction rates are much larger. There is a point here. Well, the ignition time is about 10 milliseconds in this particular study, but it is not likely to be so in most actual situations.